as a minor experiment. But before that, let's understand the concept of glass as a container. So whenever we are talking about the container, we know that it is very integral part of the formulation. And we also should know that there is no container on the earth which is totally insoluble or does not affect the contents. Okay. So when I say this, glass is also not an exception to this. So every container would have some kind of interactions with the product, but the degree of interaction can vary based on the type of container that you have selected. So on what basis do you make this selection? You want to definitely see the composition of the container. That is, what is the material, plastic, glass, rubber, closure, and then composition of the formulation, whether that formulation is going to be compatible with that composition. And second thing is treatment to which it is subjected. So whether you need to autoclave it, or you need to dry heat sterilize it, or gaseous sterilization, what is the treatment? Okay, based on that, we are supposed to select the container. So I'm talking about specifically parenteral container. So these three aspects are important: composition of the container, composition of the product, and the treatment to which it is subjected to. Having said that, glass is supposed to be the most valuable container for parenterals, valuable in terms of quality. Okay, it is not costly, but it is very important when it comes to its inertness with the formulation. It is not totally inert. There will be minute interaction, but when you compare it with plastic, this is supposed to be very good in terms of least interaction with the product. Now, glass has a basic structure of silicon oxide tetrahedron. So you may show it schematically this way. And this silicon oxide tetrahedron is the one which gives a kind of robustness, toughness to the container. So as I mentioned, it is a container or material of choice for injectables. Now it is also having some small quantities of other oxides. When we talk about glass, the principal component is silicon dioxide, which appears like this tetrahedron. Along with silicon dioxide, glass does contain number of other alkali oxides: sodium, potassium, calcium. Also, it has small amounts of magnesium, aluminum, boron, and iron. Iron when you require a colored, amber colored glass. Otherwise, you may have, or you do have these oxides, but in small quantity. So this is about the composition, and you need to know that silicon oxide forms that tetrahedron, and these other oxides, they are present in the interstices of the container. So in the sense, they are loosely bound to the entire tetrahedron. Okay, and then they are loosely bound, so they have a migratory ability. It can migrate easily from the container and can be leached into the solution. So their presence in the network interstices and its ability to relatively free to migrate in the solution, these are the two things which are required to be considered. And then when these migratory oxides can be leached into the solution in contact with the glass, especially during thermal sterilization, what can happen is they can hydrolyze sodium oxide, potassium hydroxide, potassium oxide, calcium oxide. They can hydrolyze to the respective hydroxides, and sodium NaOH, CaOH twice. Okay, so these hydroxides are going to raise the pH, and moment solution has little alkalinity, that alkali component is going to act as a catalyst for hydrolytic degradation of the drug. So these migratory oxides are required to be considered very seriously while selecting the container for parenterals. So we are going to study how do we classify the glass based on the migratory oxides present in the composition of the glass, and how do this classification impact the quality of the product. Further, how pharmacopoeia helps us to evaluate which type of glass it is, and based on that particular test, how do you differentiate between various classes of glass? This is the point of discussion when we talk about glass as a container. So as I told, these migratory oxides are going to raise the pH of the solution and catalyze the hydrolytic degradation. So then also overall, it is less, the glass is a material which is least affected by chemicals as compared to other packing material. It is impermeable to gases, solutions and solvents. When I say this, immediately there is a comparison with plastic, because plastic has this particular drawback of permeability to the gases and sorption of some components. Okay, sorption, leaching and permeability. These are the three major problems with plastic. So that way glass is impermeable to gases and solutions and solvents. So oxidative degradation will be totally, the drug can be protected from oxidative degradation if you have sealed it in glass container, because glass is not going to be permeable to the air. There are many others. So we are talking about all these advantages of glass. So least interaction, so least affected by chemicals, impermeable to gases, solutions and solvents, transparent. Then it has good thermal resistance. This point we need to consider when we are discussing parenterals, because we cannot forget that sterilization is an important step in the processing of parenterals. So the material that we have selected has to have good thermal resistance. Also, it should have good resistance for sterilization by radiation, because radiation is basically gamma radiation. So sometimes gamma radiation can be a method of choice for sterilization. And gamma radiation can lead to oxidative radicals like OH2, H2O2, OH, okay? And these radicals can further cause degradation of the drug and degradation of the container itself. So glass has resistance for any kind of degradation by radiation, and it is also resistant to any kind of chemical degradation. It is very elegant, it, sparkling clean glass is very elegant. And if you need protection from light, sometimes light can act as a catalytic factor for certain kind of degradation. There are some photolytic degradation. So in that case, when then you need to select amber colored glass, which can absorb that particular wavelength of UV, and it protects the drug from photolytic degradation. So for that, ferric oxide, manganese oxides can be used as pigments to make it amber colored. Sometimes cadmium sulfide is also used if you want a red colored glass. Then yes, because we need glass, we need ampoules to be fused. So we need to see whether it has enough softness so that it can be fused by heat. So that is possible. Complete sealing can be achieved by fusion, and this is required in ampoules. Labeling also is possible manually or mechanically. We have a lot of ceramic inks for labeling, and then direct printing possible with ceramic. This is not packaging, this is ceramic ink, sorry. And that is how glass turns out to be a very good material of choice. And yes, it doesn't deteriorate with age, and it is not very expensive, so it is economic to use glass as a material. So when there are so many advantages, what are the disadvantages? So this is a common sense that glass is fragile, it is breakable. And secondly, it is going to be heavy as compared to plastic. So there is going to be additional cost for the transport. But this fragility can be overcome by coating of glass with oxides of tin or titanium dioxide, on which you can further apply a synthetic polymer such as polyethylene oxide glycol, which helps in proper protection of the glass against its breakability. Now, we need to consider what are the different types of glasses. Now, various types of glasses are based on the resistance to water attack of unused glass container and the degree of attack being detected by the amount of alkali released from glass under conditions specified. So this particular concept is called as hydrolytic resistance. What is it? When there is a water present in the container, water attacks the glass container and the degree of attack is detected by the amount of alkali that is released from the glass under condition specified. So from where this alkali is being released, we saw in the composition of glass, there are sodium, potassium, calcium oxides. So these alkali oxides can get released when it is in contact with water, and based on the resistance to this water attack, various types of glasses are classified. So these classes are lime soda glass or type 3 glass. We are going to see what are these types. Borosilicate glass or type 1 glass, treated soda lime glass or sulfured glass or type 2 glass, siliconized glass and other types, like for example lead free glass that comes under different types. Moving on to lime soda glass or type 3 glass. So lime soda, as the name indicates, it has higher amount of sodium oxide and calcium oxide. So the principal component is always silicon dioxide, which is large in amount, around 70%. But sodium oxide is 13% and calcium oxide is 9%, which is also significantly high. And as I earlier mentioned, these alkali oxides are going to present in the interstices and they would have migratory potential. And because of this migratory potential, these oxides can be attacked or can be leached when water attacks the glass. And then when they dissolve in water to form hydroxide, that can lead to degradation by catalytic degradation, where sodium hydroxide or potassium hydroxide can act as a catalyst. Some more properties of glass. It melts at convenient temperature and it is easy to process. So we said that glass can be fused and we can seal the ampoules. So the temperature required for sealing should be such that practically it is possible to fuse it in the laboratory. So we have this advantage that glass, soda lime glass, that is type 3 glass, it's soft glass and it can conveniently be melted and you can fuse and seal the container. But the minus point, that is the con, would be that it has very low hydraulic resistance. When I say it has low hydraulic resistance, it means that it is vulnerable to attack by water, and the resultant effect of attack by water is leaching of oxides, alkali oxides. Secondly, it flakes comparatively easily. And it loses its brilliance on repeated use. So what happens is that the sodium oxide, which is leached, or rather when there is a moisture, condensed moisture on the outer wall of the container, it dissolves carbon dioxide from the atmosphere. And as this sodium carbonate attacks the glass and it causes losing of brilliance of glass. So this kind of reaction is very prominent for lime soda glass because it has higher amount of sodium oxide. So it can easily get converted to sodium carbonate, which in turn leads to leaching or flaking of glass, leading to loss of brilliance on repeated use. This is very important. Glass has high coefficient of thermal expansion. When I say it, high coefficient of thermal expansion, it means that when you heat it, it expands very rapidly and it can fracture. So this can be a problem when you are fusing the glass at the time of sealing of ampoules. You are going to practically experience it when you start filling the ampoules with injectables and sealing the ampoules. So that's a skillful job that you have to learn. And when your labs are open, you're going to first study that, prepare the solution, fill it in the ampoule without allowing the droplets of solution to stick to the neck of the ampoule, and then seal the ampule by heating it in the flame, heating the neck of the ampule in the flame. So while doing that, you need to have a type of glass which fuses easily, so that you can pull it, by pull sealing, that is, you can pull with the forceps, and then and then you can just knock it off, so that you get a proper bead at the sealing point. So this is possible because of good coefficient of thermal expansion, but this can be also detrimental, because if you heat little slightly overheated, that leads to further expansion of glass, and it just bursts there, and you get a pinhole, you get a crack. So this is a problem for type 3 glass. Now type 3 glass is further divided into, rather I must say, lime soda glass is further divided to type 3 glass. Now lime soda has two types, type 3 and type NP. Now type NP is non-parental, as the name indicates, do not use it for any parental product. But type 3 glass, okay, can be used for packing of non-aqueous injections, oily injections, because here hydrolytic resistance will not be coming into picture. There is no water in the formulation, so you can use type 3 glass. Now type NP glass is further inferior quality, more amounts of alkali oxide, less amount of silicon dioxide. So for parenteral purpose, this is not used. Type 3 glass can be used for parenterals, provided it is a non-aqueous formulation, or if you want to go for aqueous formulation, the contact of water with the container should be transient. So this can be a reconstitution type of formulation. So in the vial, you have just stored a dry powder. Before administration, you are reconstituting with water for injection and then administering to the patient. Yes, that is possible, for which you can go for type 3 glass. Why type 3? Because it is going to be substantially economic, cheaper than type 1 glass. So under these conditions, you can go for type 3, but type NP should not be used for parenterals. So this was the little inferior type, and which is a superior variety of glass, that is called as borosilicate glass or type 1 glass. As the name indicates, it is borosilicate type 1. So first class, the best quality of glass that we have for parenteral purposes. Logic is that this is going to be in contact with non-aqueous formulation which doesn't have water. So yes, you can keep a balance between the cost and the formulation quality. Now coming to type 1 glass. Now every type has some subclasses, So I must say that lime soda glass has these two classes, type 3 and type NP. Okay. Now borosilicate glass. So borosilicate glass, as the name indicates, it is supposed to be highest in the amount of silicon dioxide. Yeah. So it has a very high melting point. It has more hydrolytic resistance. Okay. Highest as compared to other two types. And then it is of course very expensive, and it has low coefficient of expansion. Why so? Because it is hard. It is comparatively tougher. So it is not going to fuse or melt very conveniently. And when it melts, it is going to melt very gradually. It is not going to show very rapid expansion followed by breaking. Okay, so it has a low coefficient of thermal expansion. So it has boric oxide in its composition. So borosilicate, 30% silicon dioxide, 12% boric oxide, aluminum oxide 2%, and sodium potassium oxides are very minimal in amount, just 6%, not even more than that. Okay, so this is supposed to have highest hydrolytic resistance. It will not be leaching alkali oxides easily when it is in presence of water. Now this glass, type 1 glass, has two subtypes, Pyrex glass and neutral glass. Now Pyrex glass, the composition that I have shown you, that is a composition of a Pyrex glass, which is very expensive and is not used most of the time. But neutral glass can be used. Now neutral glass is little inferior to Pyrex glass. When this inferiority, when we say, it is all related to alkali oxides presence and presence of silicon dioxide, boric oxide. This composition ratio, when it varies, the cost varies and the quality of glass also varies. Its degree of hydrolytic resistance varies, right? So neutral glass is little inferior to Pyrex glass, but much superior to lime soda glass. So that way it has again a good economic value for the money. So it has good hydrolytic resistance, much better than type 3 glass. It is cheaper also, and it's softer than Pyrex glass. So it is used for infusion bottles, can be also used for ampoules. So whatever ampoules we have in our college, which you are going to use, these are all of neutral glass. They are not of Pyrex glass, they are of neutral glass. So there is one more type, that is siliconized glass. So why siliconized glass? Because sometimes you may use the container for suspensions or for dry powder to be reconstituted. So after reconstitution, you need to withdraw the formulation, yeah, and then the remainder of the formulation should not stick. The particles should not stick to the glass wall. The glass wall should have clean appearance. So for that, some hydrophobicity is required to be imparted on the inner wall of the container. So what has been done here is that the containers are rinsed with liquid silicone and then they are baked in oven. This helps in binding of silicone outer side, the silicone externally, a sort of coating in the inner wall of the container, and that imparts hydrophobicity. And so we can use it for anhydrous products, suspensions, powders, and there are less chances that these particles would stick to the surface of the glass, and the glass would appear, the container, the formulation container would appear very clean and elegant, and there would be always dose uniformity. There is an intermediate type between type 1 and type 3, and that intermediate type is type 2. So this is going to enjoy the benefits of type 1 as well as type 3. Type 1, why? Because internally it has been treated in such a way that it does not leach alkali oxides. And how type 3? Because it is not as costly as type 1. It is cheaper like type 3 glass. Why? Because only the internal surface of the container, which is coming in contact with the formulation, has been treated so as to minimize the leaching of alkali oxide. But the rest of the container, the outer part of the container, it continues to be of lime soda. So it is called as treated soda lime glass. It is a treated soda lime glass. So basically it is a soda lime glass, that is type 3 glass, which has been treated with the given treatment. So lime soda glass is subjected to moist sulfur dioxide at an elevated temperature. And then what happens is that when there is a moisture present, sulfur dioxide causes leaching of sodium oxide. That migratory oxides get converted to sodium sulfate, and this sodium sulfate is further dissolved by giving a proper washing, okay, and all that sodium sulfate formed is properly removed from the inner part of the container. And the container, such container that you get, has all migratory oxides removed, and the inner surface is nicely behaving like a type 1 glass, like borosilicate glass. It will have minimal migratory oxides available on the part which remains in contact with the formulation. So this is type 2 glass, which also can be used. So you can go for neutral glass, you can go for type 2 glass when it comes to parenterals, and for anhydrous formulation, you can go for soda lime type 3 glass, not type NP. Okay. Now there are other types like lead-free glass. What is the lead-free glass? So if your formulation has EDTA that can leach out, what happens is that the formulation lead, and if the glass has small quantity of lead, then lead can get migrated to the formulation, and EDTA can immediately chelate it, and that can lead to formulation, toxicity to the formulation. So we need to, whenever your formulation has some chelating agent, you have to take care of the type of glass. Now in the glass, most of the time lead quantity will not be present, but then also you will go for a special grade of lead-free glass when you are using a formulation having EDTA, because lead-free glass will be specially tested for the freedom of lead, and it would be safer to use it for the formulation which has any kind of interaction with PVDA, possibility of interaction. Now USP classification, it goes this way. So see, in USP they have specially given another type, that soda lime glass, no, NP, and soda lime glass. So somebody asked me this question. So soda lime glass NP is not for parental. Soda lime glass can be used for parentals provided it's a non-aqueous formulation. So USP says we have 4 types: borosilicate glass, soda lime glass, treated soda lime glass, soda lime glass NP. Now coming to hydrolytic resistance test, because we have just defined type 1, type 2 and type 3 glasses, but we need to check whether the glass that is in your hand, which is used for your product, is belonging to which type of glass. You need to know how to test it for a particular type. So for that, the test that is given in the pharmacopoeia, it's called as hydrolytic resistance test. So now this test became official from 1995. And now also, currently also, you will see the same test is being used for performing for determining the type of glass. So this particular type is available for differentiating between type 1, 2 and 3. So this hydrolytic resistance test is performed in 2 stages, test 1 and test 2. Now you have to listen to me carefully, because in the practical class, it is this particular concept which would be checked by giving you a small experiment. So first understand the concept and then try to understand what kind of experiment can be given to you to test your knowledge here. So what is test 1 here in hydrolytic resistance test? This is as per IP 2010. So in this particular test, what we are going to do is, first of all, we need to know how much containers are to be selected from a particular batch. Okay. So based on the nominal capacity of container, number of containers would be selected. So this particular table is important, and you can see this is the capacity of container. Based on that, number of containers are defined, and then volume of test solution also is defined for titration. Okay. So why so many containers? Because these containers are required to be filled with water for injection. They are required to be sealed and autoclaved. And what is the significance of this particular volume? So if 20 ampoules, each containing up to 3 ml of solution, that is its capacity. So 20 such ampoules you have filled with water for injection. You have sealed these containers and you have autoclaved it. 121 degree, 20 psi, 20 minutes. After that, you are going to break open the ampoules. You are going to cool the solution contained in all 20 ampoules. So if it has, let's say, 2 ml per ampoule, you have 40 ml volume. From that 40 ml, you are going to just take 25 ml for performing a test. That is how you have to interpret this particular table. So this is a given procedure which is given in detail. Okay. So crux of it is that you fill the container with water for injection, seal the container and autoclave it. If you have a large volume parenteral, just fill it with water for injection, cover it with a Petri plate and then or borosilicate glass dish and then autoclave it. Okay. And then what next? What are you going to do is this test solution that you are going to pipette out from the pooled solution, and then you are going to titrate it against 0.01 molar hydrochloric acid using 0.15 ml of methyl red as an indicator. So obviously you are titrating against acid because you want to find out the alkali that is leached into solution. Okay, because this is a hydrolytic resistance test. Water is attacking the glass. Glass is leaching alkali. Alkali that is leached is being assessed by titration with 0.01 molar hydrochloric acid. Now, based on the reading that you get, you have a table, table 3. So when it is a type 1 or 2 glass, now that was a test solution for 25 ml. So find out how much quantity is required for 100 ml of test solution multiplied by 4 and you get this kind of table, right? So you just match your reading with this table based on the capacity of your container. Okay, that is overflow volume of your container. So what you observe here in type 3, when it is type 1 or 2 glass, the readings are pretty low. That means the tighter reading after titration with 0.01 molar hydrochloric acid, the purine reading that you are going to get is very low. But if it is type 3 glass, the reading is high. So this is as per our hypothesis that type 3 glass is going to leach alkali oxides. So it is having higher reading as compared to type 1 or 2 glass, right? And then what next? Because you could arrive at a conclusion that yes, my glass is type 3 or my glass is type 1 or 2. But now I need to know whether it is 1 or 2 because I want a specific answer to this particular question. So for that, the second part of the test 2. In the test 2, what we are going to do is, we want to nullify the effect of surface treatment of type 2 glass. Do you remember type 2 glass in what way was different than type 1? Because type 3 rather, we had treated the internal surface with sulfur dioxide, moist sulfur dioxide. And the alkali oxides were migrated and they were made free from, the surface was made free from migratory oxides. So it was just surface treatment which would come in contact with the solution. So it is very easy for us to just eliminate the effect of this internal surface treatment. How would you do that? For that, you're going to fill up all the containers with some strong acid which can actually dissolve this internal surface, dissolve or rather cause some kind of erosion of this internal surface. So we fill it with 4% volume by volume solution of hydrochloric acid and we allow the containers to stand for just 10 minutes. Okay, because it is such a strong acid that is more than enough to just overcome the effect of surface treatment. And then these containers are properly washed 5 times with water. And then we are going to perform test 1, that is hydrolytic resistance test. We are going to repeat that test. So what happens when this is done? Now type surface treated soda lime glass, that is type 2 glass, no more behaves like type 2 glass. It starts behaving like lime soda glass. It starts behaving like type 3 glass. So what are you going to do is just treat it with hydrofluoric acid, 4% volume by volume, wash it and repeat test 1. That is fill the container with water for injection, seal it, autoclave it. After autoclaving, cool the solution from the given number of containers, pipette out 25 ml of test solution and titrate against 0.01 molar acid. Now, what do you expect? If it is type 1 glass, it would not be affected by hydrofluoric acid treatment. It would give you the reading similar to what you got in test 1. So reading remains unchanged if it is type 1 glass. But if it is type 2 glass, now surface treatment has no impact because we have treated with hydrofluoric acid. This impact has been nullified. So now it has started behaving like its original composition, that is lime soda. So now when you perform test 1, the reading is going to be very high. So find out what is the reading. And now just see, in test 1, the reading was less. But in test 2, after treatment with hydrofluoric acid, reading has shot up. It means it is a type 2 glass. Reading unaffected, type 1 glass. Reading raised, type 2 glass. That is how we will differentiate between these two classes. There are some other tests, like you take a axis of the the cut piece in the cylindrical axis, mount it in the spectrophotometer cell and see the transmittance of light and check whether it can protect, it can absorb the region of UV like 290 to 450 nanometer range. What is the transmittance? And whether there is a decrease in the transmittance for the UV range. And that is how we can check its ability to protect against light. And of course, sometimes for the reason of stability, we don't use amber colored bottle, amber colored container. For example, ascorbic acid injection, It is very prone to oxidative degradation. It immediately forms dehydroascorbic acid. So for ascorbic acid injection, though it is sensitive to photolytic degradation also, we do not go for amber colored container, because the amber color is because of iron oxide or cupric oxide. So this can leach into the formulation and it can catalyze oxidative degradation. So for such containers, always you have to use, you can use a container which is covered with light, with paper or some kind of box, and opaque covering is required to be maintained till contents have been used. That kind of labeling requirement has to be there. You have to also measure the dimensions. You have to see whether it is free from any kind of surface effects like bubbles, itching, or any kind of defect. So that was about at an elevated temperature of 500 degrees centigrade.